Hello. The purpose of this video is to provide a very friendly way to factor perfect trinomials. And this is kind of a counterpart video of the shortcut we made to expanding binomials, to square binomials. So here is the key idea. We're going to begin just by factoring this, the first example, like we did in our previous video. And so we would factor using an area model. Like before, we have, let's say the first one would be x squared here and positive 25 here. And then I realized very quickly, of course, my factors of x squared are x, and factors of 5 could be 25 and 1. But if I look at my midterm of 10, it's easy for me to see that really the factor is positive 5 because the midterm is also positive. So when I do these, I end up with a factorization that looks like this, which is perfectly good, consistent with what we've done. The diagonal works. So my factor would be, or my factors in this case would be x plus 5 multiplied by x plus 5, which really is x plus 5 squared. Okay, so now let's see if we can get from the trinomial to the square binomial more efficiently, or more in a way that it makes more sense to us, or faster. Really, this makes perfect sense. It's just a faster way. The first thing we have to do is recognize when we have a perfect trinomial. And to recognize a perfect trinomial, there's a couple of very easy things for us to see. The first term and the last term are perfect squares. So anytime the first term and the last term of a trinomial are perfect squares, that's a good indication that these could be a perfect trinomial. Interesting. Now notice too that the third term is always positive. Like, we know it's always positive because when we multiply a number by itself, it doesn't matter if the number is positive or negative, the outcome is positive. So this number is always positive. And that right at the bat allows me to see that to get from the trinomial to the binomial, what I would have to do is something as simple as this. I know this is going to be a square binomial. Well, the easiest thing would be this. Find the square root of the first term, which is x squared, the square root of the last term of my trinomial, which in this case is 7. And then I need to just check one more thing. I need to check two things. Remember the way we did our, sorry, I put x squared and that's not x squared, just x, excuse me. Square root of x squared is x. And so when we did the expansion, if this was x plus 7 squared, I hope you remember that to find the middle term, all we did was take 7, multiply by x, and double that. So that means that my middle term should be 7 times x double, which is 14x. So that tells me that my factorization is correct. And it also gives me the sign that is positive for my x plus 7. So I hope you can see very quickly how easy this was to factor. First, I had to recognize that this was a perfect trinomial. I cannot do that with other trinomials. That's very important. If they're not, they didn't come from a binomial square. But once I recognize that, and to recognize that, I look at the first term and the last term, and I see if, particularly, but both have to be perfect squares. And if you notice here on the right, all these terms are perfect squares. So that is a big inkling that this is going to be um, a perfect trinomial, meaning it came from a binomial square. Then all I have to do is remember how I constructed a trinomial from a binomial square, and that reverse the process. So now that I have the trinomial, I'm going to do the square root of the first term, the square root of the last term, and then the sign of the middle. Then I have to, to just to be sure, verify that this works, because 7 times x multiplied by 2 is 14. And in this case, it works. And that's it. So let's do the next one. And hopefully, as we do these more and more, we will develop a bit of proficiency. So the square root of x squared is x. The square root of 8 is 64 is 8. Now that all I have to do is look at my middle term. And I can see already that x times 8 times 2 is 16. The only thing that I need is to realize that I need the sign of the middle, because when they would multiply and expand, I would end up with negative 16. And that's it. So to factor x squared plus 16x, minus 16x plus 64, the factorization is a binomial square, x minus 8 squared. Pretty friendly. But what about if we have something a little bit more complicated? Something like this example, where the coefficient of the x squared is not 1. Well, similarly, if it's not a 1, but it's a perfect square, and the last term is a perfect square, we know that we are dealing with a perfect trinomial, and we can apply this method irrespective of the numbers, so long as we have recognized that. So guess what? This worked for this one very easily. So the square root of 9x squared would be 3x. The square root of 16 is 4. And the sign of the middle is positive. And that is it. 3x plus 4 squared. And I can see, if I wanted to verify, that the product of 4 times 3x is 12x. When I double it, I would get 24x, which is my middle term. Perfect. And look at the one underneath, our last example, which is very, very similar. The only difference here is this. My first term is also the square root of 9x squared, which is 3x. And then the last one is also 4. However, this time my middle term is negative. And that means that I need a negative here, because when I do the product of 3x times negative 4, I would get negative 12x. Double it would be negative 24. So I hope you can see how easy it is to factor with this shortcut perfect trinomials. So remember, the key part, of course, is to recognize them. And once we recognize that this is a perfect trinomial, the methodology is very friendly. And we can easily verify, going in the opposite direction, that this works. So these methodology will be useful later when we are thinking about completing squares. Of course, these also gives us something very interesting. Each of these solutions, or these binomial squares that we just found, represent a quadratic. And in this case, we have not only the values that gives us the zeros, but we also have the vertex. This is a very interesting thing. But we're going to expand on that later. So thank you again, and we'll see you next time.